Did the universe, all 13.8 billion years of it, actually start off too fast? Now think about what that even means for a second. We've been taught this simple tale. Big Bang, tremendous heat, things expanding and cooling, stars and galaxies assembling neatly over billions of years, right? But what if I told you that James Webb, this shiny telescope sitting a million miles from Earth, is returning images and data that make it look like somebody hit fast forward on cosmic history? We're talking entire galaxies showing up in just a few 100 million years after the Big Bang. Galaxies forming stars at insane rates, black holes slamming themselves together and growing into monsters almost instantly. It's like building a skyscraper before the cement on the foundation has dried. And this throws us, scientists, cosmologists, pretty much everyone, for a loop. If that wasn't strange enough, this is where Sir Roger Penrose steps into the room. Now, we're not just talking about black holes, entropy, and the mysteries of space. We're talking about someone who spent decades asking questions that tear apart what we mean by the beginning itself. He's the guy who mathematically proved that when enough mass collapses, boom, you get singularities. Those strange punctuation marks in space-time where physics, as we know it, breaks. But then he went further. He didn't just stop at black holes. He asked the most ridiculously big question. What even is the beginning of the universe? Penrose pioneered this idea called Conformal Cyclic Cosmology. Stick with me here. Basically, he's saying the Big Bang might not have been the beginning at all. What if it was just part of an infinite chain of eons, each one born out of the ashes of the previous? Doesn't that sound impossible? Well, giddy up, because Penrose claims it's mathematically elegant, even if it freaks everybody out. But listen, before we dive into Penrose's bold ideas, let's talk about why James Webb and Roger Penrose have any reason to show up together in this conversation in the first place. See, this isn't some coincidence. Webb is showing us evidence. Galaxies like JADES-GS-C13-1 detected just 330 million years after the Big Bang, and CEERS-1019, an active black hole just 570 million years after. The kind of evidence that's making even hardcore cosmologists scratch their heads. Why so early? Why so fast? Did structure, stars, galaxies, black holes really start forming in a logical sequence like we thought? Or is some fundamental part of our picture missing? And Penrose for decades has been that poking voice in the background asking whether we've misunderstood the entire nature of space-time and cosmic beginnings. Here's the thing. Webb isn't just some better, prettier camera sending us fancier space selfies than Hubble ever did. No, it's designed for a totally different kind of science. Webb's secret weapon is infrared sensitivity. And that's not just some jargon. It's the key that unlocks the first galaxies. Here's why. When you look at really, really distant objects, the light they send you has been stretched by the expansion of the universe. A galaxy that might have been glowing brightly in ultraviolet or visible light back then, now has its light stretched all the way into infrared. That's why Webb's instruments, they've got names like NIRCam, NIRSpec MIRI, are so crucial. They're like heat-seeking devices capable of detecting the faintest red-shifted signals from across time and space. Imagine this. If Hubble was like watching a distant lighthouse through binoculars, Webb is like detecting the faint residual warmth of someone's bonfire on the cold shoreline miles away. That's how much further Webb takes us. Now, back to Penrose. The man operates in two distinct lanes, and both hit science at full throttle. First, he's the guy behind singularity theorems. These theorems prove that if you let gravity do its thing, and enough mass collapses in on itself, space-time just breaks. That's where black holes come from. And not only are these theorems foundational, they're bulletproof. Every conversation about black hole physics owes a debt to Penrose's math. But his second lane, that's where the controversy starts. Conformal Cyclic Cosmology. The idea that our universe is just one among an endless chain where each cosmic eon hands off to the next. Like runners passing a torch. It's bold, it's audacious, and yeah, it's debated. So what you're about to see in this video isn't some clickbaity claim that James Webb proved Penrose right. No, we're not here for that nonsense. Instead, think of this as a journey into two clashing, fascinating ideas. On one side, Webb is rewriting what we can see about the early universe, showing us galaxies so mature, so chemically evolved, so massive it almost feels like they shouldn't exist that early. And on the other side, Penrose is making us question whether our entire concept of the universe's starting point, even its geometry, is just scratching the surface. This video is about how Webb is sharpening the kinds of questions Penrose has been asking for decades. Questions like, why was the early universe so smooth and orderly? How does gravity's tendency to create black holes fit into the larger picture of space-time? And can the standard cosmological model known as Lambda CDM really explain the wild, fast-paced development Webb is now laying bare? Finally, here's a quick promise. Throughout this discussion, we're sticking to a rule: observations first, theories second, speculation dead last. Why? Because we don't want to fall into the trap of turning this into some sci-fi guessing game. When Webb shows us light from a galaxy, or the red shift of an active black hole, that's cold, hard data with physics behind it. When Penrose talks about entropy or space-time geometry, that's equally the product of rigorous mathematics. And when we move into the more speculative stuff, like whether the Big Bang truly was the beginning, we're going to tell you explicitly that's what we're doing. This is science, not wizardry. So with that clarity, let's dive deep, look at Webb's shockingly early galaxies, and build the case for why Penrose's biggest ideas might be more relevant now than ever. But here's the burning question that everyone's still wrestling with. Why has James Webb, just a little over a year into operations, shaken the cosmology world so much with its early galaxy findings? What's the exact root of the tension? Let's go straight to it. Webb has smashed through what we used to call the redshift frontier. It's seeing galaxies at redshifts we barely dreamed of confirming, so distant, so ancient, so primordial, that they existed just a few 100 million years after the Big Bang. JADES-GS-Z 13-1 to 330 million years old. CEERS 1019 to 570 million years after the beginning, already hosting an active black hole. Pause on that for a second. These aren't just faint smudges in the sky. These are thriving systems, some with heavy elements, some with star formation so intense they outshine massive galaxies billions of years later. What the Webb telescope is showing us feels ridiculous, almost like watching a skyscraper pop up in the middle of an empty desert just seconds after laying the foundation. The most intuitive way to think about this, and trust me, this is where most scientists kind of pause and take a deep breath, is like this. In the standard cosmological picture, galaxies take time to form and grow. Gravity pulls gas together, gas collapses, stars ignite, heavier elements form and accumulate, and billions of years later, mature galaxies light up the universe. Webb is essentially showing us that this entire process somehow got a massive head start. It's as if the seeds of cosmic complexity were planted and sprouted almost instantly after the Big Bang. It doesn't necessarily break physics, but it does put physics on notice. How is this happening so fast? How are we finding this much structure so early? These tensions won't go away by just slapping on another model tweak. Something deeper's going on. And here's the thing, claims like these don't come out of thin air. Webb is a precision instrument, but there's a key difference between its two primary methods of identifying these ancient galaxies, photometry and spectroscopy. And this difference is crucial to understanding what Webb is really showing us. Photometry is essentially measuring how bright an object appears in different filters, using that brightness to estimate distance, redshift, and even mass. And early on, a lot of Webb's impossibly early galaxy claims came from photometric candidates. The problem? Photometry is fast, but it's also less precise. A few false positives can sneak in. This is where spectroscopy enters. This is Webb's heavy artillery. Spectroscopy isn't just looking at brightness, it's splitting light into a spectrum, finding fingerprints of specific elements, Oxygen, nitrogen, hydrogen, combined with signatures like emission lines that directly lock in a galaxy's distance, its chemical composition, its formation age. Think of it this way. Photometry is taking one glance at a blurry passport photo and saying, you're probably 25 years old, but spectroscopy, that's reading your birth certificate and verifying the age down to the precise day. That's why early claims from photometry sometimes softened after spectroscopy came through. This isn't Webb failing, it's science doing what science does best, refining itself, cutting away the noise until only the truth remains. Now, let's amp up the pressure. One of the strangest things Webb is finding isn't just the existence of early galaxies, it's how these galaxies seem to form stars in bursts. Imagine this, a galaxy quickly forming billions of stars in the blink of an eye, then suddenly stopping, going quiet, and then starting up again with another big burst. It's not steady, it's sporadic. That's a big deal because our models tended to assume a smoother process, early galaxies gradually building themselves over time. But Webb is telling us those first generations of stars must have been lighting up and burning out in these wild, intense cycles. And here's the kicker. That might actually explain why so many early galaxies look so surprisingly bright. Some of them might not be enormous, they're just caught in the middle of this crazy star-forming episodes where their brightness temporarily skyrockets. It's almost like seeing a city during a New Year's fireworks show. Everything looks brighter and more chaotic than it is on a typical quiet evening. And this ties directly into another stunning detail Webb has revealed, the chemical story. Scientists expected the earliest galaxies to have lots of hydrogen and helium, which were the first elements forged in the fiery aftermath of the Big Bang. But some of the galaxies Webb has found are already enriched with heavier elements, like nitrogen. Wait, nitrogen? That shouldn't really be there yet. Heavy elements like nitrogen, carbon and oxygen are cooked up in stars through nuclear fusion. They get scattered out into space when those stars die, paving the way for the formation of rocky planets, complex chemistry and eventually life. For Webb to see nitrogen fingerprints in its spectra this far back in time means not just one but maybe 2 or more generations of stars must have lived, burned through their fuel, exploded and enriched their surroundings. Are you seeing the issue? This isn't gradual enrichment over billions of years. It's speed-running cosmic chemistry in just hundreds of millions of years. Scientists have even raised the possibility of unique, short-lived stellar populations, something so far outside what we expected that it could rewrite how we think about chemical evolution. So here's where we throw Penrose into the mix. Is this proof for his theory? But does Webb's data add fuel to one of his biggest questions? Absolutely. If the rapid emergence of complexity in the early universe seems so oddly efficient, so bizarrely fast, it makes the question of initial conditions even sharper. Penrose has long argued that the most remarkable thing about the early universe isn't just that it was hot or dense, it's that it was smooth. Smooth in terms of its gravitational structure, low in what's called gravitational entropy. And this smoothness is weird because gravity loves chaos. It loves clumps. It loves creating collapse and forming black holes. But the universe starts smooth. It starts as a clean slate. That's why we see time unfold in a forward direction, why complexity builds, and why we're here at all. Webb's findings, the bursty galaxies, the fast star formation, the enriched chemistry, they pile onto this fundamental question. Why did the universe begin with this improbable low-entropy starting condition? Penrose thinks that smooth beginning is the clue we need to expand the way we think about time, entropy, and the cycle of cosmic history. So how do we make sense of this? Webb is not offering up definitive answers. What Webb is offering is pressure that's pushing cosmology to explain how the early universe got its act together so quickly. And Penrose, decades ago, was already asking the bigger, scarier question. Maybe the way we think about beginnings, about timelines, needs a total overhaul. But let me ask you this. Why does this low entropy beginning of the universe matter so much? Why does this smoothness, this almost freakishly perfect state, haunt cosmologists? Because, as Penrose puts it, the early universe wasn't just smooth by accident, it was too smooth, almost suspiciously smooth. Let's put it into perspective. In terms of gravitational entropy, a completely chaotic, clumpy universe, a universe full of black holes and gravitational collapses, is the maximum state of disorder. That's what gravity wants. It wants to clump. You leave gravity alone for long enough, and eventually you get stars, galaxies, and black holes swallowing everything in sight, punctuated by explosions where everything falls apart. And yet, in its infancy, the universe said no. It started in a state that avoided all of that chaos for just long enough for complexity to emerge. Here's the crazy part. If you were to calculate the chances of such a low entropy beginning just randomly happening, the number is insane. Penrose once estimated it something like 1 in 10 to the power of 10 to the power of 123. Just writing that out in zeros would stretch across the universe. It's that unlikely. And yet, here we are, living in a universe that somehow began in this precise, tuned, low entropy state. And Webb is showing us how quickly that smooth beginning gave way to chaos, structure, and complexity. The obvious question is, why? Why would the universe start in such an extraordinarily unlikely state? Was it a one-off cosmic roll of the dice? Was it just luck? Or, here's where Penrose's theories start creeping in, was there some kind of deeper mechanism, something we don't yet understand, that caused such an improbable beginning to occur? Now, Penrose's take on this question isn't a simple one. It's bold, and it's complicated, but its core is deeply tied to his obsession with entropy and the arrow of time. According to him, our universe's low entropy state wasn't a result of luck or randomness. It was a result of geometry, of space-time itself. And this is where his theory of Conformal Cyclic Cosmology, or CCC, starts throwing grenades into the conversation. What Penrose suggests is that our Big Bang wasn't the ultimate beginning. Instead, it was the transition from a previous eon, a previous universe that had expanded so much for so long that everything in it smoothed out entirely, leaving behind only radiation. No masses, no complexity, just a perfectly smooth, nearly featureless geometry. And at that point, Penrose claims, scale stops being meaningful. The enormous stretched-out universe of that old eon becomes mathematically indistinguishable from the tiny, dense geometry of the new Big Bang. The cycle resets, and here we are, living in just one eon in an infinite chain of them. Does that sound wild? Yeah, of course. But it's not just Penrose waving his hands. The guy backs this up with hardcore mathematics rooted in conformal geometry. Basically, the idea that even when things are stretched or squished to absurd degrees, their shapes and causal structures might still stay the same. And that's the trick he uses to leap from one eon to the next. The infinite future of the previous universe transformed into the Big Bang of the next. It's audacious. It's speculative. But Penrose thinks it's the key to solving the entropy puzzle. So where does Webb fit into all this? Why does this shiny infrared telescope sitting a million miles away matter in a conversation about Penrose, entropy, and eons? Because Webb has become the ultimate microscope into the early universe, the exact moment where that smooth beginning we talked about started giving way to structure, gravity-driven chaos, and entropy. Jade's galaxies showing up when they shouldn't, insane bursts of star formation, chemically enriched regions popping up when no one thought they could. These findings are sharpening the big questions Penrose has spent his entire career asking. What set the rules for the universe's low entropy start? And how does that beginning connect to the growing complexity we see today? Let me give you a specific example of that connection. Take CEERS 1019, one of Webb's most extraordinary early discoveries. It's not just a distant galaxy, it's a galaxy with an active black hole, roughly 9 million times the mass of the Sun, that already existed just 570 million years after the Big Bang. Have you ever stopped to think how insane that is? Black holes don't form out of thin air. They need time, First, you need clouds of gas to collapse into stars. Then massive stars explode and their cores collapse into black holes. And even then, those black holes need to merge with others, grow by sucking in gas, and build themselves into giants over billions of years, or so we thought. Yet here's CEERS 1019, sitting there practically at the dawn of time, already flaunting a supermassive black hole like it's no big deal. This is where Penrose feels so relevant. His singularity theorems are the backbone of what we know about black holes. He proved mathematically, decades ago, that gravitational collapse doesn't just lead to bizarre objects. It leads to actual points in space-time where physics, as we understand it, breaks down. Black holes are not these weird fringe cases. They are the inevitable consequence of having a universe governed by general relativity. When enough mass collapses, space-time curves so severely that nothing, not even light, can escape. That's the kind of fundamental insight Penrose gave the scientific world. And now, here we are watching Webb uncover early black holes that formed so quickly it feels like they're cheating physics. Except they're not cheating. What they're doing is forcing us to rethink the early growth channels for black holes. How could CEERS 1019's monster have grown so big, so fast? There are a few ideas. Maybe it started as a small stellar black hole and fed furiously on surrounding gas, growing faster than we thought was possible. Maybe it formed through direct collapse, a massive cloud of gas and dust skipping the whole star formation process and collapsing straight into a black hole. Or maybe early black holes formed through rapid mergers, where clusters of stars smashed together in chaotic environments and turned into dense singularities. Here's the kicker. Webb doesn't give us all the answers yet, but it's narrowing the possibilities. Showing that whatever happened, the universe's first few 100 million years were unimaginably messy and fast-paced. And again, Penrose's questions are hanging right there in the background. Black holes are the universe's entropy champions. They are the end game of gravitational collapse, the ultimate engines of disorder. So the fact that black holes are already a part of cosmic history, so early in the timeline, brings us back to that question. How did the universe go from its astonishingly low entropy starting state, smooth, uniform, and simple, to a state where black holes, galaxies, and chaos emerge so rapidly? What does that say about the rules that govern the beginning? And now this is where the biggest, loudest claim surrounding Webb sneaks in. Did these findings break the standard cosmological model? Surely galaxies popping up and black holes crashing. The Big Bang's after party must mean something's deeply broken, right? Well, not quite, but that tension, that weirdness, it's real. And here's why it's so important. It shows us that the gap between what we observe and what we fully understand is far from closed. Science thrives in this space of tension, and Webb has just turned that tension up to a deafening roar. Here's the real question that's probably burning a hole in your brain right now. Did James Webb break the standard model of cosmology? Did the telescope do the unthinkable and smash apart the foundational framework we use to understand the universe? This Lambda CDM model, which has been the backbone of everything from the universe's age to the expansion rate and the formation of large-scale structure. The dramatic headlines you might have seen, Webb overturns Big Bang Theory, love to throw fuel on this fire, but let's cut through the noise. The actual answer is no, Webb hasn't broken the standard model. It hasn't ripped cosmology apart at its foundation. But here's where the tension goes up a notch. It has forced us to confront and refine critical pieces of that model. It's made parts of the universe's early story feel, let's just say, uncomfortably weird. Let's untangle what's happening here. First, when Webb launched, its initial results came fast and bold. There were claims of galaxies being found at impossibly high redshifts, galaxies so old and bright that they seem to break every rule. Remember those numbers? JADES-GS-Z 13-1 at 330 million years after the Big Bang, CEERS 1019 at 570 million years with an active black hole. Those were the kinds of results that had scientists scrambling. but they weren't conclusions, they were just the first sketches. Because as we said earlier, most of these initial findings came from photometry, using light brightness and filter data to estimate redshifts. And photometry, while powerful, can sometimes lead to overestimates. A galaxy can seem like it's from 300 million years after the Big Bang, but when you dig deeper with spectroscopy, which directly measures redshifts from light spectral fingerprints, it might turn out to be closer, maybe from 500 or 700 million years after. And that's exactly what happened. Some of the most dramatic claims softened after spectroscopy. Certain impossible galaxies turned out to be early, yes, but not as impossibly early as originally thought. And here's the beautiful thing about good science: it adjusts. It corrects itself without shame and improves its models and edges closer to the truth. This isn't cosmology breaking, this is cosmology working. Scientists aren't in some arm-waving panic yelling the Big Bang failed. They're analysing, refining and pinpointing. But, and this is a massive but, even after these corrections and refinements, the early universe still looks surprising. Let's be clear. There still is genuine tension building between what the standard model predicts and what Webb is observing. Even galaxies confirmed with spectroscopy, even after adjusting stellar population models, still look brighter, heavier, and more mature than you'd expect this early in cosmic history. And this is where things get wild. Webb is showing us that the universe's early timeline isn't wrong. It's just more intense and more compressed than cosmologists initially predicted. Like gravity, star formation, chemistry, and black hole physics all teamed up and decided to speedrun the early game. This tension is especially sharp when it comes to galaxy assembly. Here's the deal. Galaxies in those first few 100 million years don't just pop up out of nowhere fully formed. No matter how advanced your telescope is, the process still starts with clouds of gas that coalesce under gravity, form stars, and go through cycles of feedback, where explosions from the first stars or winds from black holes blow gas out and sometimes slow down star formation. All of this takes time. The Lambda CDM model, which stands for Lambda Cold Dark Matter, predicts how long this process should take given the universe's age, the distribution of matter, and the expansion rate. And for the most part, that model has done a damn good job explaining large-scale cosmic structure. But Webb is adding complexity. The galaxies it finds aren't contradicting Lambda CDM outright, but they are forcing scientists to ask whether we've underestimated how efficiently gas cooled, how fast stars ignited, and how clusters of matter grew into mature systems. And then there's reionization. Pause. I know that sounds technical, but hear me out because this is where it gets really juicy. Think of reionization as the universe clearing its fog. After the Big Bang, the universe was a hot, dense soup of particles, electrons, nuclei, photons. Eventually, it cooled enough for electrons and nuclei to combine and form neutral hydrogen. The universe became transparent enough for light to travel freely, and that's how we see the cosmic microwave background. But later, something dramatic happened. The first stars and galaxies produced radiation that reionized this neutral hydrogen, breaking it apart into charged particles again. That era, this fog-clearing process, is what we call reionization, and it wasn't instantaneous. It happened patch by patch, region by region, like bubbles of ionized gas carving their way through the neutral cosmic sea. Webb hasn't just been finding early galaxies here, it's been watching reionization itself unfold. Galaxies like JADES-GS-Z13-1 aren't just distant, they're actively creating transparent regions in their surroundings. And the question is, how did reionization happen so fast? For this process to accelerate, early galaxies needed to produce an immense amount of ionizing radiation, far more efficiently than previously thought. If reionization bubbles are forming this early, it means these galaxies weren't just lit, they were aggressive factories of radiation. It adds yet another layer to the story of a universe evolving much faster, much noisier, and much more dynamically than we anticipated. And you know what's absolutely fascinating? This doesn't break standard cosmology, not even close. But what it does, and this is where things get thrilling, is push the limits of what that model can comfortably handle. It forces us to fine-tune our understanding of galaxy assembly, feedback cycles, and the efficiency of star formation in ways never imagined before. And this brings us, and you, right back to Penrose. See, Penrose spent his career focused on foundational questions, not just about the timeline of the universe, but about the very fabric of its beginning. Even if Lambda CDM holds, and so far it absolutely does, Penrose's question lingers. Why was the starting point of the universe so perfect in its smoothness and low entropy that we even get galaxies, stars, and black holes at all? Webb hasn't invalidated that question, it's made it louder. It's reminding us that the universe didn't just get lucky, it had to have started in a very particular way for any of this to happen. And if that smooth beginning leads dynamically to the structures Webb is detecting so quickly, that's a pathway Penrose's framework thrives on exploring. So no, Webb hasn't smashed apart the Big Bang, it hasn't broken Lambda CDM, but what it has done is crack open one of the richest, most contested chapters of scientific discovery we've ever had, early cosmic structure. And this fight between observation and our expectations is just getting started. So here's the next big question. If James Webb hasn't shattered the standard model of cosmology, and if it hasn't handed Sir Roger Penrose a cosmic trophy saying you were right all along, then what exactly are we looking at? Where do all these early galaxies, bursts of star formation, and ridiculously rapid black hole growth leave us? Well, we're standing at the edge of two frontiers. One where Webb is pulling back the curtain on how fast the universe went from smooth to clumpy, from order to complexity, and another where Penrose's deeper, more mind-bending questions about time and beginnings start scratching at the surface of cosmology. And nowhere does that tension show up more dramatically than when we talk about black holes. Let's park here for a second, because black holes aren't just cool space objects or sci-fi fodder. They are absolute cornerstones of cosmic evolution. And Webb is putting them front and centre in a way that's forcing us to rethink how and when these gravitational beasts started influencing the universe. Take CEERS 1019 for example. This galaxy doesn't just have a black hole, it has an active black hole, consuming material like a galactic vacuum on steroids, less than 600 million years after the Big Bang. How does a black hole even grow that fast in such a short amount of time? Let's break that down, because even with cutting-edge models for black hole formation, CEERS 1019 feels like it's bending the rules of how physics works in the early universe. Here's what we generally know about black hole growth. The process starts with a seed. That seed might come from a massive star, one many dozens of times the mass of the Sun, that burns through its nuclear fuel, collapses under its own gravity, and turns into a black hole. Seed black holes like these usually start small, maybe around a few to tens of solar masses. From there, they grow in size by pulling in surrounding gas, dust, and even stars in a process called accretion. But accreting gas isn't just a straightforward stuff falls in scenario. It's messy, it's chaotic, and it comes with limits. Radiation pressure slows things down as the hot gas heats up and pushes outward. It's like trying to stuff more food into a container that's already bursting at the seams. Scientists call this the Eddington limit, and it puts a cap on how fast a black hole can grow under normal conditions. But here's the thing, CEERS 1019 doesn't seem like it cared about normal conditions. For its black hole to have reached 9 million solar masses so soon after the Big Bang, it would have had to grow at such an efficient breakneck pace that we're left wondering whether the early universe had some special tricks up its sleeve. One possibility is that this black hole didn't start as a small seed. Instead, it might have come from something called a direct collapse black hole, a much larger initial black hole, born directly from a collapsing cloud of gas and skipping the star-making stage entirely. That gives it a head start. Another possibility is that there was rapid merging, where smaller black holes combined into bigger black holes faster than expected. Or maybe, just maybe, the early conditions of the universe made accretion far more efficient, with cold gas pouring into black holes like water down a funnel before winds, radiation, and feedback mechanisms could slow everything down. And this is where Penrose resurfaces, dressed like the ghost in the machine. Because while all of these scenarios are about how black holes grow quickly, Penrose forces us to ask a bigger question. Why are black holes such key players in the universe at all? His 1965 singularity theorem, the one that won him a Nobel Prize, showed that black holes aren't just oddities, they are the inevitable result of extreme gravitational collapse. And more importantly, they're not just the doom engines of the cosmos, they're entropic engines. Remember gravitational entropy? Black holes are the kings of it. They represent the ultimate gravitational disorder, packing more entropy into their horizons than anything else in the universe. When you think about the universe transitioning from smoothness to complexity, black holes are the climax of that story. They are where gravity fully commits to chaos. So when we see black holes this early in cosmic history, it backs us into a corner. Why did the universe move so quickly toward one of its most extreme entropic states? How does this fit into this wild arrow of time journey Penrose has been talking about? The transition from a refined, low-entropy beginning to a messy, structure-filled cosmos brimming with collapsed objects. These black holes Webb is finding aren't proof of Penrose's conformal cyclic cosmology, but they are yet another piece of evidence that gravity doesn't play a passive role in cosmic history. Gravity isn't just lingering in the background. It's actively pushing the universe toward entropy, structure, and complexity, almost as soon as the cosmic clock began ticking. But here's the darker, looming twist. What ultimately happens to the entropy these black holes create? Penrose's boldest claims about black holes come into play here. In Conformal Cyclic Cosmology, black holes are more than just entropy champions. They're also the cleanup crew for the universe. See, Penrose argues that in the far, far future of our own aeon, the universe we're living in right now, all matter, structure, and mass will eventually decay or get pulled into black holes. After that, those black holes will evaporate through Hawking radiation, leaving behind essentially pure radiation. It's this final cleanup stage that allows the universe to reset itself, to go from a cold, lifeless void in one eon to a new Big Bang in the next. Now let's be absolutely clear. Webb isn't confirming that framework. Webb can't observe previous aeons or predict the far future of the universe, not directly. But what Webb is doing is putting black holes front and center in the story of cosmic evolution, showing us that these titans of entropy weren't gradually written into the storyline. They got in on the action from the ground floor, and that reinforces Penrose's larger theme. Whether you're looking at the beginning of a universe, its middle, or its end, gravity and collapse are the forces shaping everything. So now we arrive at one of the most unsettling and fascinating questions Webb and Penrose are combining to raise. If the early universe is such a rapid, chaotic, and efficient machine for creating black holes, what does that say about the conditions that existed before it? What primed the stage for this burst of complexity? Was it just the randomness of quantum fluctuations, as standard cosmology would say? Or was there some kind of deeper ordering principle that we're only beginning to glimpse, one that links the geometry of space-time itself to this bewildering efficiency in forming structure so fast, so early? And Penrose, if nothing else, would tell you this: don't just ask what the universe is made of, ask why its initial conditions were so improbably perfect in the first place. Webb keeps finding the effects. Penrose is asking us to hunt for the cause. Now, let's scale this conversation up. We've talked about black holes, star formation, enriched chemistry, and galaxies seemingly leaping into existence faster than we thought possible. But this next piece of the puzzle is even bigger. It's about not just the objects in the early universe, but the environment they're swimming in. The cosmic fog, otherwise known as the era of Reionization. And here's the paradox that will bend your brain. How did the universe go from being essentially opaque, packed with a thick sea of neutral hydrogen, to becoming clear enough that light could travel freely? Did it happen way faster than we ever imagined? Here's the scene. After the initial Big Bang and the chaotic roar of inflation, the universe cooled and entered a period called recombination around 380,000 years after the Big Bang. Electrons and protons paired up to form neutral hydrogen atoms, and for the first time ever, the universe became transparent, allowing light to travel. That light, by the way, is what we see today as the cosmic microwave background. But, and here's where things get foggy, over the next several 100 million years, that neutral hydrogen wasn't just sitting there doing nothing. The first stars and galaxies began to form, but their light couldn't travel freely because the universe was still packed with thick clouds of neutral gas. It was, in a way, like trying to shine a flashlight through a dense fog. Ionizing photons from these early stars struggled to carve through the haze. This is what astronomers call the Dark Ages. So here's the question. What finally cleared that cosmic fog? What reionized the neutral hydrogen and made the universe transparent again? The answer is energy. Tons of it. Enough to ionize hydrogen atoms across enormous stretches of the cosmos. And where does that energy come from? From the earliest stars, galaxies, and critically, active black holes spewing out powerful radiation. The process wasn't uniform. It didn't happen everywhere at the same time. Instead, it happened in pockets, or bubbles, which slowly grew and merged like cracks forming in a frozen lake under spring's first thaw. Imagine patches of light chiseling their way out of a cloudy medium, carving tunnels through the fog. That's reionization. Now here's where James Webb flips the script. Early galaxy surveys using Webb, especially with galaxies like JADES-GS-Z 13-1, are suggesting that this process of clearing the cosmic fog may have started and progressed faster than the standard model of cosmology comfortably predicts. For instance, NASA's reports indicate that galaxies existing only 330 million years after the Big Bang, extremely early, are already producing enough ionizing radiation to carve out bubbles of ionized hydrogen around them. This discovery matters because it means these galaxies were producing photons, the kind of high-energy photons that rip hydrogen atoms apart with an efficiency that's incredibly high for their age. It challenges existing assumptions about how quickly early stars and galaxies could grow, output energy, and affect their surroundings. But here's where things get stranger. Reionization wasn't just about stars. Black holes, those early gluttonous monsters we just talked about, almost certainly played a massive role. Active black holes, like the one in CEERS 1019, weren't just consuming matter and generating gravitational chaos. They were also producing unimaginable amounts of energy in the form of jets and radiation. And because black holes emit ionizing photons at a rate far higher than typical starbursts, their role in clearing reionization bubbles might have been far more important than we initially thought. Webb's ability to find galaxies with active black holes during the reionization epoch is a game changer. It's revealing that black holes weren't just byproducts of cosmic evolution. They were active participants, accelerating the timeline of how the universe became transparent. Now, let's circle back to Penrose for a second, because everything we've just said about reionization ties beautifully into his bigger obsession: the arrow of time, entropy, and how the universe transitioned from smoothness to complexity. Reionization is such a fascinating step in this process, because it shows entropy unfolding in real time, cosmically speaking. The early universe began neutral and simple, utterly featureless in its fog. Then, with the ignition of the first stars and the feeding frenzy of the first black holes, that fog didn't just dissipate, it was violently and energetically ripped apart. Energy was fed into the system, entropy rose, structures began forming with shocking efficiency, and the orderly smoothness of the early universe gave way to clumps, collisions, and complexity. It's entropy at work, all the way down. Here's an angle Penrose would want you to think about. Reionization wasn't just a random phase in cosmic history, it was inevitable, a natural outgrowth of the fact that gravity builds structure over time, and that structure inevitably produces energy, which feeds entropy. In Penrose's view, each phase of this cosmic evolution is connected. The low entropy beginning demanded a chain reaction, a universe in which energy disperses, structures form, and stars and black holes drive the universe toward higher and higher states of gravitational chaos. This isn't just about isolated observations of galaxies or photons. This is a cascade, a sequence written into space-time itself, unfolding from smooth beginnings toward the messy, dynamic universe we see today. But, and this is a huge but, here's the part that still confounds cosmologists. Why was the beginning so smooth in the first place? Why was reionization even necessary? Why did the universe start in a state where it needed to work hard to build entropy at all? Penrose points to this low entropy beginning as the deepest mystery of modern cosmology, and it's a mystery that Webb can't directly answer. Webb can show us how quickly complexity unfolded, how stars burned through their fuel, how black holes grew like wildfire, and how reionization cleared the fog. But it leaves us with the same haunting question that Penrose has been asking his entire career. What made the universe's initial conditions so special, so fine-tuned? Do you see how the tension keeps building here? Webb isn't invalidating anything, neither the Big Bang model nor Penrose's theories. Instead, it's tightening the screws on the timeline of cosmic structure formation, intensifying the scrutiny on how fast entropy and complexity emerged, and making us revisit the assumptions we've long held about the universe's early days. This is the sweet spot for science, the point where hard observations meet fundamental, unsettling questions, and we're just getting warmed up. Right, so now that we've discussed reionization, the fog clearing, the bubbles of ionized hydrogen popping up all over the universe, and the incredible role early stars and black holes played in tearing through that cosmic haze, let's crank the tension up even higher. Because if your jaw hasn't already dropped at how chaotic, fast, and efficient the early universe seems to have been, there's an even deeper layer to peel back. How those early black holes, stars, and galaxies connect to the biggest question about all of this. Not just how, but why. Why did the universe evolve this way? Why did the beginning of the universe, so smooth and so improbably well-ordered, sow the seeds for this explosion of complexity that Webb is showing us? And let me stop you right there before we move into the details. This is where Roger Penrose strikes hardest. His ideas, his obsession with entropy, with the arrow of time, with the geometry at the root of space-time itself, they don't just hover around the edges of this conversation, they cut right through its core. But before we get there, let's pause and talk about what entropy really means in the context of the universe. We've said it before, but it's worth repeating because once this sinks in, it changes the way you think about everything. Entropy is a measure of disorder, right? But it's a little counterintuitive when you bring gravity into the mix. In most systems, disorder means chaos, a scrambled mess. Like imagine dropping a deck of cards and watching them scatter across the floor. High entropy, the deck is in a disorderly state. But gravity flips the script. For gravity, disorder doesn't look like a chaotic soup. Disorder looks like collapsing objects. Stars, galaxies, black holes. It looks like clumping. High gravitational entropy is concentrated in things like black holes, where the gravitational collapse is so severe that not even light can escape. Now, here's where Penrose drops a bombshell that should make your brain itch. The early universe, the smooth, almost uniform sea of particles right after the Big Bang, was not a high entropy state. It was the opposite. It was astonishingly low in gravitational entropy. Think about that. Gravity, which loves to clump, didn't clump. It behaved itself. It let the universe stay smooth, orderly, structured, and ready to produce stars and galaxies over time. But that smoothness, that order, according to Penrose, it wasn't just curious, it was an enormous cosmic anomaly. He argued that such a low entropy start is so unlikely, so special that it demands explanation. That's really what the arrow of time boils down to. The reason time feels like it flows forward, why eggs break but don't unbreak, why stars burn but don't unburn, why your coffee cools instead of reheating itself on its own, is because the universe's beginning locked in this incredible sense of order, forcing entropy to rise over the time ever since. And now we're seeing the consequences of that low entropy start in sharper detail than ever. James Webb is essentially a time machine with hyperfocus. It's showing us exactly how that smooth beginning over just a few 100 million years gave rise to stars, galaxies, and black holes, these enormously messy entropic systems at a speed that continues to accelerate. Take the Jades and Sears observations, for example. Webb has already pinpointed several galaxies whose ionizing radiation, remember those high-energy photons, played a role in reionization, whose star formation happened in erratic bursts, and which even show signs of heavy chemical enrichment. Nitrogen, carbon, oxygen, all those elements that were supposedly rare at this stage of the universe, they're showing up in excess in certain systems. That's because the very first generations of stars, known as population 3 stars, made almost entirely of hydrogen and helium, burned hot and fast. Those stars exploded, scattered their elements, and set the chemical stage for the next wave of star formation to kick back in with more complex ingredients. This kind of rapid-fire chemical evolution feels chaotic. That's gravitational entropy at work. The universe is moving from smoothness towards structured complexity as fast as physics will allow. And then, of course, you've got the black holes growing right alongside or even inside these galaxies. In some cases, it's hard to tell what's driving what. Are the galaxies feeding their active black holes? Or are the black holes, with their enormous jets and radiation, actually influencing how their host galaxies evolve? Webb's data doesn't give us the final answer yet, but here's what we do know. For black holes to exist this early and this actively, like CEERS 1019 or others, it means the universe was astonishingly efficient at producing them. Now Penrose's big question becomes unavoidable. Why start with such low entropy in the first place, only to cascade downhill into this rapidly evolving complexity? Why was the early universe so different from its later stages? And here's where he enters his controversial territory with Conformal Cyclic Cosmology. His idea that the universe's low entropy start might not be the result of randomness or chance. Instead, he thinks it might be a geometric necessity, part of a cyclical process where each universe, or eon, essentially resets itself to a clean slate after the chaotic, high entropy end of the previous one. Let me explain that in simpler terms. Imagine you're watching a video of the universe playing in reverse. All the stars, galaxies, and black holes eventually disassemble and fade away. In the very far future, the universe is left with pretty much just radiation, stretching out thinner and thinner as the universe expands forever. According to Penrose, at this stage, the universe's geometry would simplify in such a way that time, scale, and distance basically lose their meaning. Everything smooths out again, entropy drops, and what was once a vast, nearly empty universe can be mathematically mapped to the tiny, dense beginning of a new Big Bang. And the cycle continues. Now, whether this theory is true is an open question, and trust me, not all cosmologists are convinced. Penrose's CCC suggests there might even be relics left behind from the previous eon, buried in the current universe. He famously predicted things called Hawking points, anomalous spots in the cosmic microwave background, essentially glowing embers from the evaporation of supermassive black holes in the previous eon. Some researchers claim to have found evidence of these points, others remain skeptical. The debate rages on, but where Webb comes into this is fascinating. Webb doesn't directly confirm or deny CCC. Webb can't look into previous aeons or see these so-called Hawking points, but what it can do is intensify the gravitational lens we're using to understand how the universe transitioned from low entropy smoothness to high entropy complexity, and faster than we thought. If Penrose is right, if the universe's low entropy start is connected to some larger cyclical system, then Webb's early observations fit like puzzle pieces. They show us just how dramatic and high pressure that transition has always been. So here's where we're left. We have James Webb, the ultimate observer of how the universe grew up so fast, so efficiently, and so chaotically. And we have Penrose, the theorist, asking whether the entire concept of the beginning is even real, or whether beginnings and ends are just part of a larger cycle we don't yet understand. You couldn't find a more perfect collision of ideas. Now, we've reached the part of the story where the tension truly spikes. Early galaxies, bursts of star formation, black holes exploding onto the scene faster than anything we thought possible. All of this paints a picture of a universe that's racing forward in complexity from a start so improbably low in entropy that it practically screams for explanation. But now we're going to go deeper. Let's talk about what James Webb is really doing to cosmology, not just expanding our observational reach, but forcing us to rethink some of the cosmic pillars we've taken for granted. You see, Webb isn't just a tool for analysing how the universe grew, it's also pushing us to ask the harder questions about whether the framework behind our understanding still fits. This is where the stakes get higher, and where Roger Penrose's bolder, more controversial ideas come looming back into focus. To ground this conversation, it's important to understand the standard model of cosmology, often called Lambda CDM, that's lambda cold dark matter. It's the tool we've used to piece together the universe's timeline up until now, and honestly it's done a remarkable job. It explains things like the expansion of the universe, the patterns in the cosmic microwave background, and the formation of large-scale structures over billions of years. But here's where Webb pokes at it. Lambda CDM doesn't just explain the broad strokes. It makes predictions. It predicts when galaxies should start forming, how they should evolve, and how structure emerges under the influence of dark matter, gas dynamics, and time. And for years, those predictions align pretty well with observations. But Webb is shining a floodlight on the universe's earliest chapters, the part of the timeline that Lambda CDM honestly hasn't been stress-tested that deeply on until now. And the results? They are not flat-out contradictions, but they are stretching key parts of the model to its limits, like a rope pulled tighter than anyone anticipated. Early galaxies are brighter, more massive, and more chemically evolved than expected. Black holes are bigger, more active, and more numerous than anyone thought could reasonably form in just the first few 100 million years. Look, nobody's burning their Lambda CDM textbooks yet, but this isn't just fine-tuning. It's scientists asking, what are we missing? Can the physics we know explain this kind of acceleration? Or is something else, something deeper at work here? So, let's dig into one of the most fascinating pressure points in this discussion: galaxy assembly. Webb's findings have thrown a wrench into our understanding of how galaxies build themselves. Here's the standard picture. It all starts with dark matter. Dark matter makes up most of the universe's matter content. Though we can't see it directly, it's like the scaffolding of the cosmos, creating gravitational wells where gas can collect, cool down, and form stars. Over time, this process snowballs. Galaxies collide, merge, and grow into the spiraling behemoths we see today. But in the very earliest universe, this process was supposed to be delicate and gradual. James Webb just obliterated that expectation. The galaxies it's detecting are already massive, some containing billions of stars just a few hundred million years after the Big Bang. For comparison, if the universe were a human being, these galaxies would have been building skyscrapers by the age of 3 weeks. And the weirdest part, many of these galaxies aren't just regular clumps of stars, they're messy, diverse systems teeming with activity, chemical complexity, and even structures that look like disks. This early stage complexity raises a fundamental point. Whatever physics was driving galaxy assembly, it wasn't dragging its feet. It was sprinting, pulling mechanisms out of its cosmic toolbox that we don't yet fully understand. And let's not forget the most eyebrow-raising twist. The stars in these galaxies aren't just the pristine hydrogen and helium burners we might have expected in the earliest epochs. They're already chemically enriched, containing heavier elements like nitrogen and oxygen, elements that can only be forged in the cores of previous generations of stars. What this means is that some of these galaxies aren't even hosting the first stars, they're hosting multiple generations of stars that have already lived, exploded, and passed their material onto the next wave. Stop and think about that for a second. The timeline is shrinking faster than anyone thought possible. Somehow enough stars formed, lived out their lifetimes, went supernova, and seeded the next batch of stars with heavy elements, all in a cosmic blink of an eye. This takes us back to Penrose's fundamental question about entropy, about why the universe started in such a way that allowed all of this to happen. Remember, the reason things feel weird isn't just that we're finding early galaxies or that black holes are growing fast, it's that the entire trajectory from smoothness to complexity feels shockingly compressed. And while Lambda CDM can handle some of this tension, Penrose wants to zoom out and ask whether there's something about our initial conditions, our cosmic starting point, that we're fundamentally missing. Now it's easy to frame all of this as a battle between Webb's data and Lambda CDM's predictions. That tension is real, but the bigger picture is even stranger. What Webb is doing is turning up the heat on the assumption that our universe is a one-shot story, that it began in one miraculous low-entropy state and then exploded forward into structure and time. This is where Penrose's Conformal Cyclic Cosmology cuts back into the conversation like a razor. His idea isn't that Webb disproves Lambda CDM, it's that Webb sharpens the most uncomfortable and unresolved part of our standard cosmic narrative. Why did the universe get its incredibly low-entropy start? Why was it so perfectly poised to build stars, galaxies, black holes, and everything we see? For Penrose, CCC offers an audacious answer. Maybe the smooth low-entropy start wasn't a one-off event. Maybe it's part of a cycle where the end of one eon sets up the conditions for the next. That's what his theory tries to explain, using conformal geometry to link the far-flung future of one universe to the dense, energetic beginning of the next. But, and this is critical, Penrose's theory isn't universally accepted. While it solves the entropy puzzle in a mathematically elegant way, the empirical evidence is thin. Those Hawking points he predicted in the cosmic microwave background, the data is debated. Some scientists think they've seen them. Others argue the signals are statistical noise, nothing special. Webb isn't solving that debate directly. It's not designed to look for Hawking points. But here's what it's doing. It's creating more pressure to answer whether our understanding of cosmic beginnings is truly complete. This is where things get fascinating, because Webb's findings, those early galaxies and black holes, that shockingly compressed timeline, don't outright prove Penrose right, but they do make the bigger philosophical question of why this beginning and not some other feel unavoidable. If the physical universe builds complexity this quickly and efficiently, understanding those starting conditions goes beyond theoretical curiosity. It becomes one of the deepest questions we can ask. And here's where I'll leave you for now. When we look at Webb's discoveries through the lens of Penrose's questions, we're not just seeing galaxies and black holes, we're seeing the evidence of a universe that behaves almost suspiciously like it's moving along a preordained pathway, one where gravitational entropy rises, structure emerges with startling speed, and cosmology is forced to interrogate just how miraculous our beginnings really were. Alright, so here's where the story ramps up even further. Let's pull all of these threads together. The early galaxies that Webb is finding, black holes growing like cosmic weeds, bursts of star formation happening faster than the universe's own models told us to expect, and this incredibly strange question lurking in the background. Why did it all begin so smoothly, so low in entropy, almost like the conditions were handmade for structure to emerge at lightning speed? And now, let's press on toward the big picture, because we've been dancing around it, but we haven't directly tackled the ultimate tension in this entire conversation, and it's the question you've probably been waiting for. Is the universe actually telling us there's something fundamentally far deeper than the way we model time and history itself? What Webb is really doing, and what Sir Roger Penrose has been asking for decades, is forcing us to think about the one thing no one really likes to touch head on. What came before? What came before everything? The Big Bang, the galaxies, the black holes? Was there a before, or are our concepts of beginnings and endings just too limited to tackle the full scale of what might actually be happening across eons of time? Here's the paradox to think about. If the universe started in such a finely tuned low entropy state, What set up those conditions? Random chance? A multiverse scenario where it's just one lucky roll of the dice? Or, this is what Penrose leans on, was there something about the universe itself that can, in a sense, reset? Not in the sense that it just reboots everything like a computer getting turned off and back on, but in a way where the end of one system flows naturally, inevitably into the beginning of the next. That is the basic framework of conformal cyclic cosmology, the boldest and most controversial of Penrose's contributions to cosmology. Now, we've touched on its basics already, but let's really dig into the meat of it, because Webb's discoveries, while not direct proof of CCC, give us a completely new lens to understand why Penrose's ideas won't stay silent in these conversations about the ultimate origins of structure, entropy, and complexity. So, at the heart of CCC is Penrose's claim that the universe's far future looks downright boring. Think about it. Fast forward far enough in time, billions and trillions of years from now, and most of the universe's stars will burn out. The black holes will dominate at first, swallowing whatever remains, but even they won't last forever. Thanks to Hawking radiation, the slow leaking of mass and energy from black holes over unimaginable amounts of time, Penrose argues that every black hole in the universe will ultimately evaporate. What's left when that happens? Essentially only radiation. No stars, no black holes, no galaxies, no clumps of matter, just smooth, incredibly diffuse energy stretched out across an incomprehensibly large and expanding space. Okay, at this point you're probably thinking, fine, so the far future is cold, smooth and boring. How does that leap to a new universe? This is where Penrose pulls out the most audacious card in his whole idea: conformal geometry. The basic concept isn't as scary as the name sounds. Conformal geometry focuses on shapes and angles without caring about absolute size. You can stretch something larger or shrink it smaller, but as long as its fundamental shape is intact, the rules of conformal geometry still apply. What Penrose has argued is that when the universe is dominated only by radiation in the far future, when individual scales like big or small lose their actual meaning, the structure of that universe can map seamlessly onto the dense initial conditions at the start of the next Big Bang. Scale becomes irrelevant. The geometry of the universe folds into itself, forming a bridge between the infinite future of one aeon and the fiery beginning of the next. Now, if your first reaction is that this sounds more like science fiction than science, you're not alone. When CCC first emerged as a formal theory, it raised eyebrows across the cosmology world. And for good reason. Testing something like this is extremely difficult. You can't exactly rewind the universe 14 billion years and overlay it with Penrose's mathematical predictions. And yet, here's the kicker. The theory doesn't exist in a vacuum. Its mathematics are consistent with much of what we already know about relativity, thermodynamics, and quantum mechanics. And Penrose even claims his theory makes empirical predictions, like those mysterious Hawking points we talked about earlier, faint signals in the cosmic microwave background that could represent the final death throes of black holes from the previous eon. But here's the critical part, and this is exactly why James Webb is such a game changer in this conversation. CCC is not about Webb directly proving its predictions. Webb can't see relics from prior eons or measure the universe's future geometry, but what Webb is doing is erasing the simplistic comfort we had about the Big Bang being a smooth, self-contained story. It's pushing against the timeline, asking us to explain why structure developed so furiously so early, and why the universe's initial conditions seem to have been so improbably fine-tuned for all of this complexity to emerge. Penrose, for all his radical proposals, is asking the same thing. Was that fine-tuning random, or was it inevitable in some deeper cyclical framework? Now let me be clear, none of this means Penrose has been proven right. CCC is still speculative, and a lot of cosmologists roll their eyes at even the faintest whiff of something that involves previous universes. But what it does mean is that the questions Webb is forcing us to confront about the universe's speed, complexity, and entropy tie directly back to the problem CCC is trying to solve. What selected those initial conditions? Why didn't the universe start clumpy and chaotic? Why was it so smooth, and why did gravity so quickly swing it toward collapse and chaos? Webb, in its first year of operations alone, has given us wild insight into the speed and nature of early star and galaxy formation. But maybe, without realizing it, Webb is also reigniting some ancient questions, the kind Penrose has been forcing us to stare at for decades. We began this video with a simple tension. Why do the earliest parts of the universe look so fast? But now we're ending with something far more unsettling. What if the speed of the early universe, and its almost miraculous fit for creating complexity, isn't just about physics unfolding? What if it's telling us that the universe's beginning wasn't really the beginning at all? Here we are, standing right at the edge of possibly the biggest question of all. What if the beginning of the universe we know wasn't actually the beginning? What if the Big Bang wasn't some magical one-off event that came out of nowhere, but instead just one chapter, one transition in an infinite cosmic story that we're barely starting to grasp? That's what Penrose, through his Conformal Cyclic Cosmology, wants us to consider. And, whether you agree with him or not, the questions Webb is raising about the universe's infancy, how fast structure formed, how early complexity emerged, and the bewildering why behind the universe's starting conditions are pouring gasoline on that fire. So let's keep going, let's dive even deeper into this frontier where Webb's observations collide head-on with Penrose's radical ideas. Let's start with the simplest and strangest question of them all. Why does time flow the way it does? Why does it feel like time has this one-way arrow, moving forward, where cause leads to effect? Stars burn but don't unburn, and black holes grow but don't uncollapse. If the laws of physics don't actually care which direction time flows, they work just as well running backward as forward. What's enforcing this strangeness? Why doesn't the universe just loop in on itself in ways that make our forward experience of time meaningless? This might sound abstract, but it's exactly what makes the universe's smooth low entropy beginning such a big deal. Here's the core idea that Penrose and many others wrestle with. The forward flow of time, what we call the arrow of time, only exists because the universe started in an incredibly special state. Remember, entropy is disorder, and the second law of thermodynamics tells us that in a closed system, entropy always increases. Things fall apart, structures decay, systems run down, but for entropy to rise, there has to be room for it to grow. For the universe to go from low entropy to high entropy, it actually needed to start smooth, orderly, and improbably special. That initial state to Penrose is the ultimate clue, the smoking gun, that there's something we're missing about the big picture. And that's why he spent so much of his career asking, how did the universe get to that starting line in the first place? But don't just take Penrose's word for it. This isn't abstract philosophy, it's baked into physics. Let's go back to black holes one more time, because they're the ultimate players in this entropy game. Black holes represent the maximum gravitational entropy, the state of extreme collapse and disorder that gravity inevitably drives systems toward if left unchecked. The universe today, with its clusters of galaxies, its stars, its black holes, is light years away from the smooth sea of particles that existed 13.8 billion years ago. And Webb is proving just how fast that transition happened. It's showing us that black holes, gravitational collapse, and high entropy structures kicked into gear astonishingly early. That acceleration from smoothness to complexity didn't take billions of years. It started happening in hundreds of millions. This is real, observed, measurable entropy in action. But the big question, the Penrose question, is why we weren't already there. Why didn't the universe start clumpy, full of gravitational wells, high-energy black holes, and collapsed structures? If gravity loves to clump and grow entropy, why was the early universe smooth at all? That's the mystery, and it's where Penrose's Conformal Cyclic Cosmology steps in to offer its bold and controversial idea. Think about this. In the standard Lambda CDM model, we say the Big Bang marks the beginning of space-time. It's not just the beginning of the stuff in the universe, it's the beginning of time itself. Penrose argues, though, that this isn't the whole story. He claims the universe might not be a one-shot timeline bursting out of nowhere. Instead, in CCC, the Big Bang was a continuation, the next step after the far-flung future of a previous eon. In this model, every aeon ends with the universe stretching out so much that all matter and structure essentially disappear. What's left in the very end is radiation. Here's the key trick. Massless radiation, unlike matter, doesn't experience time or scale in the way we do. When everything in the universe is thinned out and dissolved into radiation, the idea of size loses all meaning. Penrose uses conformal geometry to show that at this extreme far future scale, the universe's geometry becomes mathematically equivalent to its extremely dense early scale at a Big Bang. It's a kind of space-time rebirth. The end of one eon transitions naturally, and perhaps inevitably, into the birth of the next. Now obviously the first pushback is, where's the proof? Sure, CCC is based on clean mathematics and ideas about entropy, but where's the observational hook? That's where Penrose points to the cosmic microwave background, the afterglow of the Big Bang itself. If CCC is correct, then traces of a previous eon might be visible in the faint temperature fluctuations of the CMB, specifically in the form of what Penrose and his collaborators call Hawking points. These are hypothesized to be tiny, faint spots left by the evaporation of supermassive black holes in the prior eon. If you remember, Hawking radiation causes black holes to slowly leak, and in CCC, the largest black holes in one aeon could leave behind a signature signal in the next. Some researchers claim they've found evidence of these points, statistical anomalies in the CMB that might fit Penrose's predictions. Others argue the data isn't compelling or can be explained by noise. This is one of those fierce scientific battlegrounds where the stakes are enormous, but the jury is still very much out. And honestly, this is exactly what makes the discussion so rich. Penrose doesn't have a smoking gun yet, but the fact that his ideas even touch parts of observable phenomena, like the CMB, is why we're still talking seriously about CCC at all. Here's where James Webb comes back into all of this. Webb isn't directly testing CCC, and it wasn't designed to look for Hawking points or relics of prior eons. But what Webb does is force us to reckon with how startlingly efficient the universe is at moving along this entropy pathway, how early stars exploded, enriched their surroundings, and fueled the repeated cycles of order and chaos. It makes you wonder, if this transition from low entropy to high entropy, this furious explosion of complexity, feels so systematic, is it possible that this kind of behavior isn't unique to our universe? Is it possible it's part of a larger repeating cycle? Webb doesn't answer that question, but it makes the question feel harder to ignore. So here's where we land. The first galaxies, the first black holes, the chemical fingerprints, the speed of structure, all of it confirms that the universe's first few 100 million years weren't just a leisurely beginning. They were fast, dynamic, and chaotic in ways we're only now appreciating. Webb has tightened the timeline to a point that makes cosmological models sit uncomfortably close to their limits. And at the same time, Roger Penrose keeps asking the most unsettling yet stunning question of all. What if the Big Bang wasn't the grand start? What if it was just a transition, one among an endless series of cosmic moments stretching back and forward forever? Penrose doesn't claim to have all the answers. Webb isn't delivering his theory on a silver platter. But together, Webb's unmatched ability to probe the fine details of the early universe, and Penrose's relentless pursuit of the why behind time and entropy feel less like competing stories and more like two parallel tracks converging on the same fundamental mystery: the deeper nature of space-time, beginnings, and our place in this vast, cycling cosmos. All right, let's tie everything together and push this conversation to its final frontier, where the questions become almost too big and yet too important to ignore. Let's pick back up with Penrose, the Big Bang, James Webb, and this saddening, magnificent universe we're all trying to figure out. At this point, we've laid the groundwork for something important, the idea that James Webb's discoveries, while they don't directly prove or disprove Penrose's theories, are pushing us toward a bigger reckoning. They're adding urgency to questions that cosmology has kept simmering in the background for decades. Was the universe's beginning truly special, or was it inevitable? And if it was inevitable, what deeper rules or cycles might govern the universe beyond anything we've yet imagined? Here's the thing. While Webb isn't proving CCC, let's be clear on that, it is exposing the mechanics of a universe that seems intensely purposeful in how it evolves complexity. Webb is revealing galaxies, black holes, and physics that are pushing against the limits of our current theories, yes, but they're also laying bare how quickly and forcefully the universe transitioned from its pristine beginning to this tangled web of stars, matter, entropy, and structure. The sheer speed at which this complexity emerged makes the question of why this beginning even harder to dismiss. You can't just write it off as random chance. Penrose has been telling us this for years, starting conditions matter. And Webb is writing that message in infrared light across time and space. Now let's return to that fundamental tension. What if this wasn't the beginning? What if what we think of as special or improbable about the Big Bang isn't unique at all, but is just one link in an eternal chain? That's the audacious idea at the core of conformal cyclic cosmology. Let's simplify it again for clarity. Each universe or eon starts smooth, low entropy and ready to explode into complexity. Over trillions of years, it builds stars, galaxies, black holes, and then gradually fades into a thin, smooth sea of radiation. And then, the punchline, the very geometry of that smooth, massless radiation becomes indistinguishable from the dense, hot singularity that kicks off the next universe. It's not that time begins again, it's that time, scale, and structure are woven into an endless loop. Penrose is saying the Big Bang wasn't some miraculous one-off event, it's just what universes do. Now here's a critical counterpoint. As poetic as this idea sounds, most scientists will remind you that cosmology lives or dies by data. If a theory doesn't make predictions that can be tested, it risks being philosophy, not science. This is why Penrose's CCC stands on shaky ground for some. Those predicted Hawking points we talked about, the supposed remnants of black holes from a prior eon, are highly controversial. Some analyses of the cosmic microwave background have suggested faint signatures that could line up with these points, but the statistical significance and methods used to extract them are hotly debated. Many scientists argue the anomalies are better explained by random noise or data processing quirks. Penrose would argue it's no coincidence that they align with his model, but others strongly disagree. The jury is still very much out, but Webb doesn't live in statistical noise. It lives in raw, observable, measurable details of the universe as it actually is. What Webb shows us, with those impossibly early galaxies, those supercharged black holes, and that astonishingly fast star formation, is that something about the universe's initial conditions was undeniably primed for this. And here's why this matters. If the universe builds itself this quickly, this aggressively, and this efficiently, you can't help but feel like there's an even bigger story we don't yet fully grasp. Penrose's CCC, for all its boldness, does provide a possible framework for explaining why things feel so tuned, not in the sense of a creator's hand, but in the sense of something emergent, something cyclical, built into the very geometry of space-time itself. But what Webb is also making clear is the messiness of the universe's evolution. This isn't some pristine cosmic clockwork with all the answers pre-written. It's chaotic. Some galaxies seem brighter and heavier than we expected because star formation was bursting in wild, uneven cycles. Some black holes seem impossibly large because the early universe, for reasons we still don't fully understand, must have been astonishingly efficient at feeding them. And some of the Reionization bubbles Webb is mapping suggest that radiation from stars and black holes started carving their way through the cosmic fog at a faster, more aggressive pace than models predict. Combine all this, and you start to see why Penrose's focus on entropy feels so relevant. The universe's story is always a story of chaos emerging from order, entropy rising, systems breaking down, complexity rushing to fill the gaps. But remember this, Penrose's CCC doesn't outright contradict the standard model of cosmology. It doesn't say the Big Bang didn't happen. What it does is zoom out to an even larger scale and ask whether our Big Bang is, in fact, part of something infinite. And right now, Webb's brand new data is telling us two things at once. First, it's providing stunning evidence for how cosmic history unfolded, from the pristine smoothness of the early universe to the rich complexity we see today. But second, it's sharpening the questions about why this particular history. Why this beginning smooth and low entropy, allowing entropy to rise so explosively from the start? Why did gravity, chemistry, and space-time align in a way that allows the universe to race forward? To Penrose, the smooth beginning isn't some miraculous accident of this universe, it's the natural reset of a cycle without end. And while Webb isn't directly proving this, it's making the big question impossible to avoid. Are the universe's rules not just randomly emerging from one singularity, but wrapped up in something far deeper, something inexorable? Something that demands we rethink not just the timeline of cosmic history, but the framework of time itself. So here's where we leave this video, not with answers, but with sharper, bolder questions. Webb has turned the earliest chapters of universal history into the most explosive area of modern astrophysics. It's showing us a universe that grows fast, messily, and chaotically into structure and complexity. Governed by rules we're only beginning to probe with clarity. Penrose? He remains the voice insisting we've only scratched the surface, that if the universe's arrow of time and low entropy beginning feel too special, it's because we're still missing the fundamental truth. Webb is pulling open the curtains on the universe's earliest act, and Penrose is standing back, asking if we've yet glimpsed the cosmic stage beyond. What both Webb and Penrose make clear is this: the universe, its beginnings, its structure, its fate, isn't just an object of awe. It's still, after all this time, a mystery. Maybe the greatest one we'll ever face, and that's where we stop, for now. But the questions don't stop here. They never do. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.